What is an impulse? That was our second question. Well, the impulse, as we know it here, the impulse is what? The impulse is essentially an external impulse that is time varying. So how do I write this thing here? The impulse is the integral of a time varying force. In other words, when I write the impulse, which is J, this integral from 1 to 2 is really an integral of a time varying force. So what do I mean by that? Well, what I want to do here is that I want to give you a sense of what I have here. And the way I'm going to do this here is that I want to play a video for you. Okay? So check out this video that I have. It's a very short video. Of course, I got this off of YouTube. And yes, I did pirate it. So I downloaded it and then I edited this thing. So I'm assuming that you are seeing my video right now. So one of the things that you want to look at here is this. What you want to look at is that look what happens to the ball as it interacts with this bat. Okay, so check it out. Here we go. Look how the ball is being deformed. Note that this does not happen over a single moment. And then I'll run it and then it unexpands. And then you can even see the ball wobble. Right? So the bat is applying a impulse force on this thing. So what I want to do here is that I want to go in and I want to look at this thing carefully here. So what I'm seeing here is that I'm seeing this thing here. Let me see if I could bring this in. So here's the image that we just saw right now. And what you're seeing here at this point, what you have here is that you have contact begins between the ball and the bat. And then you're seeing as the ball is being squished, and it looks like at this point here, you might have maximum compression of the ball. And then the ball leaves the bat here. So I'm going to say here is that contact ends right here. So the thing that's really, really important, and I'll only look at half of this thing. Check this out. Compare this moment to this moment to that moment. You're seeing a time varying compression of the ball. In other words, this force is not constant. So the question is, how do we draw this? And the way we draw this here is that we draw a curve. Now, the curve that I'm drawing here is a force of function of time. And if I was to try to draw exactly what we're seeing here, here's what I'm seeing here. I'm going to get a point that maybe looks something like this. Now, this curve is not correct for the baseball, but we're going to assume that it is. And I'll try to explain here in probably tomorrow or something. So what you're seeing here is that I have a curve like this. Why do I have a curve like this? because the impulse is the integral of f of t dt. Wait a minute, what does this mean? Check it out. This is what? An area. So the impulse actually represents the area under the force versus time curve. So if I look at this thing, look at this point right here. This point right here is where contact begins. This point here, I'm going to say that contact ends. And then the peak here, this point here, tells me that this is where I have maximum compression. And so what we find here is that we typically define a time. It's the time for when it starts to when it ends. This time right here, where contact begins and ends, is this delta t. This is what we call the contact time. And it's very characteristic of what actually occurs in that system. So now what I'd like to do here is that now the problem with this curve here, or this impulse curve, is that it's really hard to deal with. It's difficult to deal with because you have to parameterize that curve. So for conceptual, what we do conceptually is we typically don't use that curve. Now we could make approximations to the curve, right? One can make approximations to this curve, assuming that is, and one way that you might think about this, it may look something like this here. You could imagine that I have an impulse curve, and here it goes. So I'm going to look at this guy, and let's say that it looks something like this. So if I look at that, I'm going like, okay, here's my impulse curve. I mean, we could come in here in theory and go, well, maybe if I pick a triangular curve, it becomes a good approximation, right? If I'm looking at this thing here. So maybe I could say that the impulse curve can be approximated with a triangle. Yeah, that's possible. And, you'd have to, again, pick it really carefully. However, that still doesn't help us. The only way you can really do this is that you have to use the mean value theorem for integrals. So to get the exact value of the area, one uses the mean value theorem for integrals. And so when you use that, what you find here is it essentially does this thing here. So graphically, it does it like this. So I have a curve, okay? And as I have this curve, I have my impulse curve. Let's say this is it right here. And of course, I'm going to shade this because the impulse is always about the area. So I know I have this curve for a fact. So what you do with so when I look at the mean value theorem, it says this. So I know that the area of this guy between point 1 and point 2 must be this guy right here. So once again, this is the area of a time bearing force. What the mean value theorem does is it says, I'm not going to do that. What I'm going to do is that I'm going to calculate something called an average force. So the average force is this here. So I look at the area of red. I need to recreate the exact same area. And let's say that this is the exact same area. So then I create a rectangle. And that rectangle in blue has the exact same area as the, impulse curve in red. So when I look at this guy, what the mean value theorem says is that I can get something called an average. And then I look at the exact same time interval. So when I look at this time interval, of course, it's between the exact same times. And then the height of this thing is what they call the average force during the collision. So then this guy here is the area of a so-called constant average force. So if you can do that, then what this tells us here is that we can then calculate it much easily. But the important thing about this statement right here is that this is easier to deal with conceptually as well as mathematically. Okay, so that's really the big deal about that mean value theorem. And you'll see that a lot of the times I'm going to use that mean value theorem just to interpret what's going on.